what is quantum mechanics and why is it so important?
Well, quantum mechanics is really a theory that is treated as an inconvenience nowadays. We don't understand it very well, but we still have to use it in order to explain how things work. So it's important because there are many physical effects that need quantum mechanical description. So the stability of atoms, for example, is the main thing. So electrons going around the nucleus. If it was classical theory, then this wouldn't be a stable trajectory. We'll have emissions of electromagnetic waves. But due to quantum mechanics, these trajectories of electrons are stable. So atoms are stable, our matter is stable. So as we know, it exists due to quantum mechanics.
So what makes quantum mechanics so difficult to explain and so difficult to understand?
Well, usually people have a problem with the wave function. Every object in classical mechanics, it corresponds to a measurable quantity. We have position of a particle. If we differentiate it, we get velocity. We can measure that. If we differentiate velocity, we get acceleration. We can measure that as well. But in quantum mechanics, that's not the case. We have the wave function at some point, but there is not any measurable quantity associated to it. We can take the absolute value squared, which is a probability, and that we can measure, but wave function by itself is a peculiar concept. So we have to accept it as a mathematical inconvenience.
So is quantum mechanics a perfect theory, or are there certain aspects to it that may be missing?
Well, it's missing our acceptance. We just have to accept it for what it is. I mean, people are fighting it so hard and always picking up on it. I mean, this is sort of bullying, right? Scientific bullying that's happening. It's different, but it still works, and it does its work fine. So I think we just need to accept it.
So is quantum mechanics practically useful beyond intellectual enrichment?
Yes, so eventually quantum effects will play a role on our technological advances. Now we really want to miniaturize things. In computers, we want to go to smaller and smaller processors, or we are dealing with nanotechnology, how we can manipulate atoms and make atomic scale structures. Quantum mechanical effects will be there eventually, so we have to understand them and embrace them. Also, quantum mechanics is met in various processes like photosynthesis, and the sense of smell is predominantly quantum mechanical, as well as the navigation of birds has quantum effects in it. But we have to understand that these effects will happen even if quantum mechanics wasn't there.
Are there any direct benefits to us, to the funding of research into quantum mechanics?
I believe that it will. So directly, we depend on security. Either it's our banks that we put our pins and the passwords we use to communicate with computers. So if somebody had discovered the quantum computer and could break in that way our classical cryptographic protocols, then we do need to know about that. We do need to invest in it and try to secure them. Either being able to break them ourselves as well, or build a system which is efficient enough to protect. So yes, we may not have a quantum computer on our desk to play quantum games, but definitely we want our governments to have a quantum computer.
So if quantum mechanics doesn't eventually result in major changes to our lives, do you think it may be money wasted?
Well, funding research is like gambling, but unlike gambling at casinos, the research gambler always wins at the end. So we do need to invest. We don't know how it will go, but if it works, then there's a big gain to society. I think it would be a shame, actually a big mistake, a terrible mistake, if we were worried and would try to fund only theories that we're certain that will work. We need this element of adventure.
Are you guilty of spending money researching quantum mechanics? And what is it that you are researching?
Yes, so I'm employed to work on this topic, which I like very much. I'm interested about geometrical and topological quantum mechanics, geometrical topological effects that take place in the quantum systems.
Well, what are the differences between topology and geometry in classical mechanics, which we all know, compared to quantum mechanics, which is more abstract?
Geometry and topology are more of mathematical ideas. So geometry describes the objects, like in terms of the length, the curvature, and so on. Topology cares also about the description of objects, but not the geometrical descriptions. For example, if you have two strings, two looping strings, if the strings are looping one around the other or not, if they're entangled or not. So this is a topological characteristic, while the exact shape of the strings is a geometrical one. So you have a distinction between the two. And surprisingly, such effects do emerge in quantum mechanics. So I'm very much interested in this topic.
So how do you go about conceptualizing topology and geometry in quantum mechanics?
It's rather tricky. So, for example, you need a complicated enough system in order to have geometrical and topological effects to emerge. But if you could have topological properties in a quantum system, it means that its geometrical characteristics will not bother it. So if you make some geometrical manipulations or variations in your system, its topological properties will stay the same. So, for example, if you have two particles and you're looking at their world lines, if the world lines braid around each other, then you have a change in their wave function. But if the wave function does not depend on the exact shape of the world lines, then it's exclusively topological, it's not geometrical. And this invariance in geometrical behaviors is useful because we can say that errors change the geometry of your system, but not the topology. So you created a quantum system that is resilient against errors. And that's very useful for quantum computation.
So you once again mentioned a wave function, which you say you can't really explain. So why exactly is this interesting to someone like me, and why should I care about this overcomplicated quantum mechanic principle?
Well, if at the end we want to build a quantum computer that has certain variety of different applications, then we need to care about quantum mechanics, and we need to care about how to protect against errors. So what I advertise, what I support, is that topological quantum systems actually can beat errors and can create a computer that is resilient against errors. Errors are the main obstacle on our way to building quantum computers, so we need to find a way around errors. I believe that's the way to do it.
So something most people recognize is our good friend gravity. Can gravity be explained by quantum mechanics?
Oh, gravity is still an open problem. Quantum gravity, quantizing gravity is unsolved. I remember some 20 years ago when I was a young scientist and still wild in ideas, I tried to solve this problem. I worked on quantizing Young-Mills gauge fields, and then I thought to apply the methods to gravity. And what I found is that after quantizing gravity, you get back the classical gravity. So it was a bit of a surprise to me and quite interesting. So I communicated my result to Professor Roman Jakiv at MIT, where I was at that time. And he looked at me a bit puzzled and he said, but we expect to discover gravitational waves. So how can you claim that quantum gravity becomes classical? And that baffled me, that puzzled me at that time.
So is there a gravitational particle?
Well, I mean, the thing is that gravitational waves are solutions of the classical Einstein equations of general relativity. So the whole thing is still classical. So in order to quantize it, to make a particle out of it, is yet another step that we have to achieve. But gravitational waves are classical. They're like electromagnetic waves, like light, that classically is described as a wave.
General relativity was one of Einstein's big achievements. Was Albert Einstein wrong of his skepticism of quantum mechanics?
Well, as I said, all ideas have to be entertained in research, right? It's a big gamble. And Einstein was listening to quantum mechanics. He believed that quantum mechanics is rather incomplete. They need something in order to look more like classical. He famously said that God doesn't play dice. He didn't like this probabilistic aspect of quantum mechanics. So he fought very hard against it. For example, we know due to Heisenberg's uncertainty principle, we can't measure the momentum and the position of a particle with infinite accuracy. So together with some colleagues, Podolsky and Rosen, he devised a very, very clever scheme. Let's say two particles that have a common wave function, and I can measure the position of one particle and then the momentum of the other particle. But as I measure the position of one, the position of the other is known exactly. And as I measure the momentum of the other, the momentum of the first particle is known exactly. In that case, you contradict Heisenberg's uncertainty principle. So he was trying to introduce the idea of hidden variables that will complement quantum mechanics and will explain it and make it like classical mechanics. Now, this later on made many experiments and tried to verify or disprove his claim. And up to now, all experiments on this EPR, Einstein-Podolsky-Rosen paradox experiments, they fall in favor of quantum mechanics, and there is no any classical description. But there are still loopholes. We haven't concluded yet this discussion. If Einstein was still alive, I'm sure he would claim that there is still things to research, more experiments to be done, and people are working hard on that now.
So what is the EPR paradox, and what does it mean?
Right, yes. So the idea is that, let's take Alice and Bob. Each one has two particles, one particle each. And this set of two particles is described by a common wave function. Now, as soon as both particles are described by the same wave function, they cannot be treated as separate entities. They are all together. They are treated as one object. So if you measure the position of one, then you know also the position of the other. If you measure the momentum of one, then you know the momentum of the other. So the paradox was this spooky action from a distance that instantaneously you measure the position, even if you didn't know before, and you know also the position of the other particle, even if you didn't measure it then. So this instantaneous communication of the information due to the collapse of the wave function puzzled Einstein. He was the one who claimed that information travels with the speed of light. So he said, oh, I got you there. That can't happen.
So why can information only travel at the speed of light? Why can't it travel any faster?
So useful information can travel with the speed of light. Light is the upper velocity we have. We can't travel anything faster than that. Now, physical events can happen with a higher velocity, like the collapse of the wave function, that it's instantaneous everywhere in space. But it cannot be used to communicate useful information. So in order to do that, use the EPR states, these entangled states as we call them, in order to communicate information, you do need to have a priori communication between the parties, which always happens with a speed or lower than the speed of light. So everything is bounded by the speed of light.
So is general relativity, which describes gravity, in any way compatible with quantum mechanics?
We have not found a theory that combines the two together, quantum mechanics and general relativity. And the reason we don't have such a theory is mainly the lack of experiments. The detection of gravitational waves is pretty amazing experiment and it's pretty amazing discovery, but still in the classical realm. We can't make any more accurate experiments yet on gravity, on general relativity, to detect deviations that will force us to adopt one theory instead of the other. So we still wait for it to happen.